Hi everyone, welcome to the Arithmetic Zone. Here we have a problem for you guys. Can you find the derivative of this really complex looking equation? And for this video, you will need some knowledge on implicit differentiation, as well as just some general math knowledge that you may have forgotten from your algebra days. So you might want to brush up on that and watch our latest video if you have not, so that we can adequately address this problem. So I've just copied down the problem again on this new slide. We're going to find the derivative of the equation with respect to x, of course. And in our latest video, what we would have done is we would take our ddx, we would take this derivative and treat it as if it were our arithmetic operator, and we're going to take the derivative of both sides. I'm taking the derivative of 8y cubed. That's just 24y squared. And then, or dy dx, we can't forget that part because this is implicit. And but taking the derivative of this right-hand side looks like it's going to be a real Herculean task because it's going to be a quotient rule. You have a numerator term and this denominator term filled with x's, so you're going to have to use the quotient rule. With this numerator, we have a product rule. But to take the derivative of this would be a product rule and the chain rule, since this is all under a radical. And this would be a chain rule and another chain rule within a product rule in our denominator. So it's really just not a good time when it comes to our standard implicit differentiation. So to address this, we're going to use a new technique that's called logarithmic differentiation. And this is a pretty useful technique when you want to parse such a complex equation like this one. And it involves taking the natural log, which we're going to express as ln, of both sides. The natural log is what's used in calculus since it's a standardized log. We don't really use log base like 10, for example. So instead of taking the derivative of both sides, what we're first going to do is take ln of this left-hand side and ln of this right-hand side. So now at first glance, you may be thinking, why do we want to do this? Why do we want to take the natural log of both sides? Isn't this making this already complex equation more complicated, or just adding more stuff to it? It'd be more stuff to parse. Well, using some of our log properties, we can actually break this down into a much more suitable form. And our first log property that we're going to go over is if you have ln of a over b, a fraction within the natural log, like we do on this right-hand side, you can break it up into ln of a minus ln of b, ln of the numerator minus ln of the denominator, so you're not left with that fraction. So let's just apply that to our equation here. We have ln of 8y squared, or cubed. This left-hand side is not going to change. Now we have ln of this numerator, x squared times the radical of 2x to the 7th minus 6x squared plus 7 minus ln of 3x plus 5 to the 5th power. You want to be careful with these parentheses, especially when dealing with logs, times the square root of 9x cubed plus 4. And now it's time for another log property to further break this down. When you have a product within your ln, just as we have here, both of these have products within it, you can break this down into ln of a plus ln of b. Cool, we're going to do that with our logs on the right-hand side. This left-hand side is going to stay the exact same. And now we're going to break this up. We have ln of x squared plus ln, and I'm going to do a bit of a weird move here. I'm going to write this radical as 2x to the 7th minus 6x squared plus 7, taking everything within that radical and raising it to the 1/2. It expresses the same thing. It's just going to look a bit weird. But there is a reason why I'm doing this. Now I'm going to have minus. And actually, this is going to be a bit big. So I'm going to bring it down here. Minus ln of, where are we? Okay. 3x plus 5 to the fifth power minus ln of, and I'm going to do the same thing here, 9x cubed plus 4 to the 1/2 power instead of writing it as that radical. And I made both of these negative because of this negative sign here. Everything that we do to this natural log, its result is going to be negative both pieces. So I'm going to take all this work that we just did, and I'm just going to copy it so that we can bring it over to our next blank slide. And I'm just going to copy and paste it right here. Now for our third log property. If you have the natural log of some number raised to an exponent power, you can bring this exponent b, over here outside of the natural log and just multiply it over to get b ln of a. So once again, this left-hand side is going to be the exact same. Ln of 8y cubed going to be equal to, we're going to have 2 ln of x plus 1/2 ln of whatever was still in there. And that's actually why I pulled out the 1/2 instead of writing it as a radical, so that it's more readily apparent that I'm really pulling out this 1/2 and putting it in front. That's where the 1/2 came from. Minus 5 ln of whatever is inside, minus 1/2 for ln, can't forget that, of whatever was inside. Great. Now we can actually start our differentiation process. We're going to take our ddx and apply it to this whole equation. And the derivative of the natural log is actually pretty simple. If we have ln of u, let's say, and we're taking the derivative with respect to u, I'm doing this so that it doesn't become an implicit differentiation problem all on its own. We're going to take the derivative of whatever was inside that natural log function, and then we're just going to divide it by what was originally inside. So let's start with the process of doing the derivative of this equation. So the derivative of 8y cubed is 24, let me write that in black, 24y squared over what was originally inside, 8y cubed, and because this is a y, we're going to have our dy dx. Then we're going to have 2 over x, 2 times 1 over x, so I'm just going to put that as 2 over x, plus 1/2 times our constant multiple rule. We have to take the derivative of what's inside the log function, so that's going to be 14x to the 6 minus 12x, the 7 is 0, it doesn't have a derivative, over what was originally inside. Now we're going to do the same thing with this negative 5. The derivative of 3x plus 5 is just 3, and we're going to put our original statement in our denominator, minus 1/2. The derivative of this is 27x squared over 9x cubed plus 4. Now we go on with the process of simplifying. 24 divided by 8 is 3, and y squared over y cubed is 1 over y. So we're just going to put this as 3 over y, bring this dy dx down. Now we have 2 over x, plus we're going to multiply this fraction. We have 4x to the 7th minus 12x squared plus 7, or plus 14. And this denominator, or rather this numerator, does not change. And it's the opposite with this one over here. We have negative 15 on the top, the denominator stays unchanged, minus 18 cubed plus 8 over 27x squared. Now we could do some further simplification, and we're running out of space here. Whoops. We're running out of space here, so I'm gonna copy all the work that, whoops, sorry about that. I'm gonna copy all the work that we did here and we're gonna bring it over to this next slide. We're gonna continue this again. So some of these fractions can be reduced. We're gonna bring this left-hand side, keep it the same. 2 over x is pretty reduced here. All of these terms in this fraction are divisible by 2. So we can go ahead and reduce that. We can just divide everything by 2. I don't think we can really simplify that fraction much more. And 15 over 3x plus 5, you can't really simplify that down further. And you also can't really simplify this down further, so we're just gonna rewrite it as it is. Now we're gonna go through the process of isolating this dy dx. So we're gonna multiply both sides by y to get rid of this y here in our denominator. So we're gonna have 3 dy dx is equal to y times this whole mess on our right-hand side, right there. And then we're gonna divide by 3 on both sides to get a final answer of this whole term right here. I'm gonna copy and paste it again so that I don't have to rewrite it. All divided by 3. And I will say that's not really the proper answer, or proper final answer, I should say, because you could simplify further by using some advanced algebraic techniques to further reduce this whole mess of fractions in our numerator. And you technically can express this y in terms of x if you were to isolate this y here originally. But to be quite honest, you don't really need to, because this is implicit differentiation. If you got here and you got an answer that resembles this, you should be really proud of yourself. And I will say, if you did not use logarithmic differentiation and you didn't break it down using our different log techniques, and you went ahead doing the process of quotient rule, product rule, etc., your final answer may look different than my final answer here. I apologize if you heard those Discord notifications, but your final answer may look different than mine here, but they should still be mathematically equivalent. So anyways, guys, great job if you were actually able to get through this, and I hope to see you guys in a future video. Thank you so much for stopping by.